Hello and welcome to this lecture on vector calculus. In this video, we are going to solve problems on solenoidal and irrotational. First, we will see the basic concepts, then we will go for the problem. See, a vector field F, it is said to be solenoidal if a gradient dot F vector is equal to 0. Then we say it is solenoidal. So, this means a field has zero divergence. So, let it is typically represent incompressible flow like a magnetic field. First, we will see a general forms. Let I may take F vector equal to F1 I cap plus F2 j cap plus F3 k cap. Then, how do you write this gradient at F vector? It will be dou F1 by dou x1 plus dou F2 by dou y plus dou F3 by dou z. If this is equal to 0, then I will get the value and then I will say this vector field is solenoidal. That means all the values should get 0 because there is a sum of 3. So each of this differentiation should be 0. Then only it is possible to get finally 0. Let me go for a problem. First, we want to check whether this field is solenoidal or not. So, what is the formula for it? Gradient dot F vector equal to be 0. That means dou F1 by dou x plus dou F2 by dou y plus dou F3 by dou z. If I differentiate this function with respect to z, okay. So, what you will get this with respect to x na 2x. And with respect to y, here it will be 2y. With respect to z, it will be 2z. So, it is not possible to get 0. It will be of x plus y plus z. Okay. So, therefore, it is not solenoidal. Then, we will solve one more problem. We have to check whether it is solenoidal or not. First, we will find the gradient f vector. It will be dou f1 by dou x, dou f1 or f2, f3. That means for our representation, this will be f1, f2, f3. Dou y, dou f3 by dou z. Here it will be this. If I differentiate with respect to x, it becomes 0. Now if I differentiate f2 with respect to y, there is no y term, it becomes 0. If I differentiate the third term with respect to z, 0. So finally you will get 0. The gradient f vector becomes 0 now. It is solenoidal. Okay. Next, we will see about irrotation. When the vector field is said to be irrotational, means the gradient, a scalar product, f vector should be 0. So this represents the field has no curl, 0 curl or no rotation. So then we will see some general form. If I am taking that f vector as like this, the scalar product will be like a determinant of a matrix ijk dou by dou x, dou by dou y, dou by dou z, and f1, f2, f3. Okay, then we will solve a problem. So what we want to choose here, it is irrotational means a scalar product. That means I, j, k. On the next line, dou by dou x, dou by dou y, dou by dou z. Here it will be f1, f2, f3. Here f1 will be x, f2 will be y, f3 will be z. How do you find the determinant? I vector. I will leave this column and row. Then remaining dou by dou y of z minus dou by dou y z of y minus j vector. Next, I will leave this column and this row. So it will be dou by dou x of z minus dou by dou z of x plus k vector. It will be this column and this row. Then dou by dou x of f3. f3 will be z minus dou by dou y of x. See here, I have to differentiate z with respect to y. No, it is not possible. No? Okay. So surely we'll get 0, and with respect to this always 0, and this it is not, everything is not possible. No, simply everything you will get 0 plus k vector into 0. So finally you will get 0. Therefore it is irrotational. 0 vector is simply 0. Next, we want to check whether this is irrotational or not. Similarly, we will find the matrix, and here it will be I vector into dou y by dou y of x minus dou z of y. Okay, and minus j equal to dou x of x minus dou z of y plus k vector into dou x of z minus dou y of y. If I differentiate this, I will get the value z with respect to, if I take this over dou y by, if I differentiate the x with respect to y, it becomes 0. And if I differentiate z with respect to z, it becomes 1. So here it is 1. So minus 1, as similarly, you will get this. Finally, I am getting minus I minus j minus k. Okay, so it is not equal to 0, therefore it is not irrotational. Okay.